All right, well, let's go ahead and get started. Welcome back. Happy week number 3 of the semester. Just as a reminder, with regards to our weekly schedule and how things are going, here we are, and we are roughly following the schedule. We're on week 3. This is more MIPS control flow. I think would be a more accurate way to describe it. We've already covered some MIPS control flow last week. And as a reminder that when you go to Canvas and you click on the schedule link, um, you get access to the PDF uploads for the actual lecture notes. So that today's lecture notes are there in week number 3. The videos that we record while we're here together, and that's just recording my stream, so you're not accidentally getting recorded, even if you have some FaceTime here during the lecture itself, as well as other things that, as I find the time, just little extra sort of add-on things. So I last week I provided a brief overview of using the Mars MIPS simulator, which you will be using here very shortly, and then a separate example that looks at array addressing in MIPS. We did a brief example in class. It was fine. It was appropriate and accurate. There's a more advanced example there. And that's every week I'll be doing that. So that's the easiest place to go if you want access to both the class videos as well as the lecture notes that we have on a week to week basis. So far, we have been following the schedule and it's going okay. I'm learning a little bit more about Canvas quizzes and how to do these appropriately. I think quiz 3 will be easier than quiz 2 in terms of being able to get the right answers for things, which was always my intention. We do have that midterm coming up. We'll talk about that soon. I'm learning more about what is appropriate to put on a Canvas administered exam, and I think I'll have something figured out at least by the night before that exam is live. So, um, otherwise, let's continue on with the topics we have been covering. Um, the big one is really understanding MIPS control flow and understanding the different ways you can go from not just PC to PC plus 4, but then from PC to somewhat arbitrary additional program counter value to support things like if statements and branches in our code and while loops and things that we trust in our higher level programming languages, but we have to sort of directly instrument when we're working at the assembly level. We talked briefly about some of the architectural implications of the various classes of instructions that we have supported to date. And I mentioned we were going to keep kind of jumping down to this microarchitectural level and then coming back up to the ISA level as we introduce new ISA pieces. I will try. It tends to be kind of hastily scribbled. I'll try to show my understanding of the basic implementation strategy at the microarchitectural level, and this is a version of the processor to date in terms of what we understand. We know that the ISA is dictating those 32-bit registers for the integer register file in MIPS. And we talked about how that requirement of being able to read two values and then write a value for a single instruction, like our add instruction, uh, directly implies an organization of our register file that looks something like this, where you have ports to specify our read addresses, our source addresses, and ports that are output ports for our actual source data, and then corresponding ports for the destination address and our write data. There'd be more control signals there, like for resetting the registers or for a write enable port, because not every instruction needs to write to the register file. There'd be a clock input there as well. But conceptually, that's what our register file would effectively need to look like to support those arithmetic instructions that we saw at the beginning of last week. And then we also saw that there is implied some sort of arithmetic and logic unit, as all processors would have, to directly implement the functions needed by those individual instructions. So it can do your add, it can do your subtract, it can also do your XOR, OR, AND gate, those 32-bit operators that would be needed for those instructions there as well. It does the basic math for you. So we drew a version of this in which these two inputs of the ALU were directly connected to SData1 and SData2 of the register file. And that's fine. That's a good starter implementation strategy. By the end of lab number 3, you will have something that looks effectively like that. And then finally, we also were talking about the MIPS memory model. And I understand this is one of those somewhat complicated topics, but the way I always look at that is the ISA provides this view of memory that there's just this linear array of 2 to the 32 bytes. But oftentimes we are wanting to access data that is a multiple of a byte. So oftentimes, right, our words are 32 bits, they're 4 bytes. So we're wanting to access 4 bytes at a time. So our load instructions and load word in this case, our task as the assembly developer is to write the code needed to generate the address for that load word using shifts and adds, as well as the constant offset that the load word instruction allows you to have. And then architecturally, this is our only view of what's ultimately happening. The load word is generating that address, and then we're reading that data back from this somewhat idealized memory to get back into the register file as our W data corresponding to the destination register for that load word instruction. And then I said finally, but finally, as we've started to talk about control flow and what that would mean architecturally, we've started to briefly talk about the program counter, which is not part of the 32-bit registers in the general purpose register file for integer MIPS operation. That's an architectural or an ISA decision. Other ISAs do have the program counter be part of the register file, and it's just a register like anything else. In MIPS, it's not. It's this separate register that is not directly accessible via software. It's just a register in your implementation that you need to be able to keep track of. And we do have this fetch, decode, execute cycle in which the fetching is a reading of 32 bits from memory corresponding to instructions. The decode is determining what that instruction is and what it's supposed to be doing. We haven't talked a lot about that, and it's not that complicated, but we'll get more into that starting today and going into Wednesday. And then the execute part of the cycle, which is, okay, I've determined what the instruction is supposed to be. Now let's make sure all the right muxes get driven. The ALU is doing the operation it's required to do. And then somewhat hidden in this edge, this transition between execution and fetching, is determining what the next instruction is supposed to be. By default, as we have our linear array of bytes in memory, same as for data as it is for instructions, we'd be going from an instruction located here on this line to the next instruction located on this line in memory. We'd be increasing by 4 bytes at a time. That is why on Friday, when I was starting to draw that out, we had this program counter and we connected it to an adder, uh, and that was adding +4 to the current value of the program counter. So it was PC equals PC +4 as sort of the default mode of operation. If it's an instruction that doesn't change control flow, we know what the next one is going to be. It's going to be PC equals PC +4, whatever instruction that corresponds to in memory. That's also why it's referred to as a program counter. I said for historic reasons, it is a counter. It is counting through memory. That's referred to as a counter circuit. A register and a constant adder is an up counter. It's going up through memory and it's just increasing PC to PC +4 until there's a reason for it to do something else. And that doing something else is how we would then implement the things like the branch instructions and the jump instructions. And we haven't gotten into that yet. We have a little time before we need to get into that. Um, so this is our somewhat high level view of what's happening architecturally. We're making some progress in implementing that in the labs. So you could argue that some version of an ALU is what you're implementing in lab number 2. And then certainly this register file is what you'll be implementing in lab number 3. This interface to memory is what you'll be implementing in lab number 4. And we're bootstrapping it and we're adding that functionality to our MIPS processor implementation, and you're being able to implement more and more complicated sequences of instructions as you add these functional units to each other in your design. Lab number 2 has proven to be the boot camp I sort of designed it to be. I saw lots of activity over the weekend on people working hard on it, getting stuck in some places. The idea was, at least my idea in designing these labs, is that in lab number 2, you really should be, to the extent you struggle at all, and I don't want anyone to really struggle, but to the extent you're struggling at all, it's with understanding the tools, understanding things like syntax of VHDL, why this semicolon needs to go here, why I have to call this label something different than that other label. And that's most of what I was seeing. Understanding the foibles of model sim, of which there are many, and there's new ones created every day. Understanding the very low-level syntactical things in VHDL, and just overcoming those. And so for everyone who felt that, oh well, let me ping the TAs over the weekend, let me hop into office hours channel, let me get a quick debug help here. That's by design. That's the goal. So never feel guilty for asking for that kind of help. Sometimes my response is, well, why don't you think about it a little bit? Or here's my answer, process that a little bit and then we can walk through the code together. But otherwise that is kind of the idea that you're not just getting help from the TAs, we're helping each other out. You're asking questions and someone will say, "Oh, I ran into that same exact syntax issue 2 days ago. Here's how I overcame it." That allows us to get through the lab number 2 stuff um, and implementing this ALU, which is a relatively simple circuit, right? That ripple carry adder we've designed, and then allows us to transition. It's a gradual thing, but allows us to transition into lab number 3 and lab number 4, where my hope is that the type of questions you'll have are more microarchitectural questions. How do I implement this write enable port on these registers? That's a microarchitectural question, or at least it's a digital logic question. Not as many questions of I'm getting a component not bound error. Everyone's gotten it many times. You should now have some ideas as to what may be causing that. They can take a little while to track down. But that's the thought that we went through this boot camp, or we're going through this boot camp for lab number 2, and our complexity of the designs are going up, but hopefully your struggle with both the tool and the syntax of VHDL is going down. And so our design complexity can increase quite a bit. I don't know what the sweet spot is this semester. My experience has been lab number 3 is the hardest one of the semester. Lab number 2 is a bit of a grind in terms of there's just a lot of things you have to get through, and those syntax errors can cost you minutes or hours if you're not careful at a time. Lab number 3, I don't tell you how to do it. I say implement this. And so there's both microarchitectural questions as well as potentially still some syntax and tooling questions that you're dealing with. And then lab number 4 is relatively easy, I think, compared to lab number 3. So in terms of what we are planning, what I'm hoping to cover this week, and it's not that long of a topic, so I plan on continuing on the control flow instructions, the additional branches and jumps like that. And then if you look at the textbook, that second half, that latter half of chapter 2, it starts to talk a lot about the machine level encoding of those individual instructions. To the extent that's an interesting topic, it's a necessary topic to understand some of the design philosophy of the MIPS ISA, as well as you do need to be pretty fluent in that machine representation to be able to do an implementation of the MIPS ISA. And that's what that section is really talking about. It introduces some additional instructions like the ones we've been covering and talks a lot about the different binary formats for those instructions. We can go through it as a class together relatively quickly. In my opinion, because I can't cover it all anyway. No matter what, there's a decent number of these instructions. There's some gotchas in terms of how they're encoded at a binary level. There is that aspect of the textbook that just covers that in exhaustive detail. You never need to have it memorized. We'll focus on the big picture design decisions that were made. When it comes time to implement it, you'll need that spreadsheet. You'll need that actual representation that tells you exactly where the ones and zeros go. So in terms of control flow, where we left off on Friday, we were just talking about support for the two basic branch instructions, the branch equal and the branch not equal. And this is something of their RTL level or pseudocode level description of what they are trying to do. And they're as described. They are checking some equality between two registers. And depending on which one is which, it's checking if they're equal to each other or not equal to each other, and it's effectively the equivalent of a go-to. It's make my next instruction the one described by this label L, and that's a label in your assembly code based on whether or not at the time I execute this branch instruction, these two registers have the same value for branch equal. Or alternately, if it's branch not equal, if these two registers don't have the same value. That's called a branch or a conditional branch or a conditional jump. Depending on which resource you read, you'll hear different terms for that. But that's the idea, is that there's a condition associated with it. I want to change my control flow based on some condition. In this case, an equality condition. In this case, a not equal condition. What's not shown here is sort of the else side of what happens with that branch, which is, if the condition is true, take the branch. Next instruction is whatever that label points to. But you always have to remember what happens on the else side. If the condition isn't true for those conditional branch instructions, we're still back to PC equals PC plus 4. So that's part of our implementation strategy. If you had a branch and it's not meant to be taken because register 1 is not the same as register 2 for branch equal, our next instruction should be that fall through case, whatever happened to be next in our code. And we have to write our code accordingly that if we don't want to fall through, we need to make sure that that next instruction after the branch is something that leaves, that gets us further away from whatever those fall through instructions are. And so that's also a common design pattern you'll see, a branch for an if case followed by an unconditional branch or an unconditional jump or just a jump instruction that says, well, if the branch wasn't true, I need to jump out of here entirely. I need to just leave this function entirely or just go further away here. And that has an even simpler looking syntax, just jump to label. That's unconditional. No matter what, when you reach that instruction and you're decoding and now executing that instruction, your next program counter should be whatever program counter is encoded by that label. And we'll have to talk about what that means because there is no actual L in your implementation. Right? There's no text label that is being looked at in implementation. It's going to correspond to a program counter value. It's going to correspond to a 30-bit instruction, 32-bit instruction memory address, but how we encode that from our assembly representation that just has a label for human readability to the 32-bit machine code equivalent for machine readability is something that we'll have to cover. That video I posted about using Mars and you should get started with Mars and understanding the MIPS simulator, it does a pretty good job of showing that in action. It doesn't explain the why of why it looks that way, but it's a very clear set of examples as you run code that I have a label, I'm branching or jumping to it. What does that mean in terms of the instruction encoding? And that's a good way to verify your assumptions. Is the instruction doing what I think it's doing? If there's any debate, if the textbook is ambiguous, if I posted something that doesn't seem quite right, for this class and certainly this semester, Mars is our final adjudicator here. If Mars says it looks like this, then it looks like that. So be it. On this slide, there are a few additional jump instructions that we will have to get to. We may wait till next week to really get to them in detail, but they make, to some extent, some intuitive sense. Certainly this first one does. So if jump is just jumping to a label that gets encoded in the instruction itself, jump register is take the actual value that's stored in our register file and overwrite the PC with whatever that value is. That's why it's referred to as jump register. Jump to a location encoded in a register. And that has a somewhat analogous instruction, the and link variant of jump instructions, which is jump to a label like we're doing up here, but then also keep track of where we were by storing it in a register referred to as RA in our general register file here. What it means to keep track of that is something we'll talk about, and the value of these and link instructions is something we will definitely talk about next week. But one takeaway from this is that we talk about how the register 0 is a special one in our register file. Is a special one in our register file because it always has the value 0. It's not something that it suggests. It would be nice if the register 0 always had the value 0. The ISA for a MIPS processor has 0 in the 0 register. There is actually also, in this case, a second register in the integer register file. I don't recall which number it is. It might be 30 or 31. We'll have to remember that eventually, but it might be 31, I think. That has the label of RA for return address. That is also dictated by the ISA as having this special functionality. Because nowhere in this actual instruction does it have the word RA in it. You're not referring to RA, you're not mentioning RA in here. The instruction is literally just this, jump and link to this label, but the actual implementation of it involves updating the value of RA. So there are these two instructions, two registers that are part of the 32 registers that you're implementing for lab number 3, but then there's 2 of them you have to be somewhat more careful with how you implement them. Implementing the 0 register is going to be a pretty trivial thing. Just don't take it out of reset, or just don't even implement a register, just hardwire it to zeros. Anything will work for that. You can't really screw that up as long as you don't override it with some actual value. RA is going to require a little bit more thought in terms of how do I actually implement that functionality. Fortunately, that we have several weeks before we have to actually build that functionality in the lab. As a brief breather here, so someone's asking if does MIPS not do overloading of opcodes? To be slightly more precise, It does do overloading of opcodes because opcodes refer to the binary field in our 32-bit instruction encoding, and there is quite a bit of overloading of those, as we will see. It doesn't do that sort of aliasing of instructions that other architectures do, where there's actually just a single branch instruction. And then whether it's a branch equal or a branch not equal is based on some condition code, some extra flag that gets set in the instruction. That's not how MIPS does it. That quite a few other ISAs do it in that fashion, where there isn't actually a branch equal and a branch not equal instruction. There's just a branch instruction, and then you set the condition codes accordingly to check at runtime whether there was an equal condition or a not equal condition. A lot of other RISC processors do it in that fashion. So branch equal and branch not equal, in fact, do have different opcodes in MIPS. They're completely different instructions. That is definitely a design choice that was made, possibly as a relic of the generation in which MIPS was developed. But there are relatively very few branch instructions in MIPS. In fact, the table lists several more of these, and we don't actually implement any of these in the lab, so I don't get too excited about them, but there actually isn't a branch less than instruction. If you want the equivalent of a branch less than operation, which is a very common thing, right? We would very often want to do um, the equivalent of a branch less than, right? Where logically, at least in our code, we would want to do branch less than, register one, register two, off to some label. Unfortunately, or fortunately or unfortunately, uh, this doesn't have its own opcode, in MIPS at least. This is not an instruction that is directly supported in MIPS. Now, you will see code examples that use this all the time. Again, because it's a very common thing, right? This is the equivalent of in our C code, we would just want if, A is less than B, right? Followed by go to or whatever functionality is inside those that if block. Very common and natural functionality we'd want to be able to do, but it doesn't exist as a native instruction. What MIPS as an ISA or at least as an assembly language we program with allow us to do is to implement several so-called pseudo instructions. It's a little tricky answering a question is whether the pseudo instructions are part of the ISA or not. I actually don't have a really firm answer to that question because ultimately what happens is these pseudo instructions are not natively implemented in your microarchitecture. You are not writing any logic in VHDL, for example, that is implementing a branch less than instruction. It doesn't have its own opcode. It's not an instruction. It is very useful functionality to have, right? So I'm kind of speaking out of both sides of my mouth here, right? It's a very useful functionality to have. If A less than B is a very natural thing we want to do in our code all the time in C, so in recognizing that, we recognize, well, wouldn't it be nice if we had a branch less than instruction? What will happen is if you were to write this in your mips.s file, the assembler would actually, in its assembling pass, as it translates your assembly instructions down to those 32-bit instructions, is going to expand upon those assembly instructions that are pseudo instructions. And there's a number of them because there's a lot of things that MIPS doesn't natively support that are very useful to have in your assembly coding. And it's going to replace it by an equivalent sequence of native instructions. In this case, this was Friday, that feels like years ago, but we did already briefly talk about that, right? That as a design philosophy, the MIPS folks said fewer instructions is better. That was that reduced instruction set. Every time we can just kind of get rid of having an unnecessary instruction, our decode logic gets a lot smaller. The assemblers, which were written by hand back then, can be that much simpler. That was the risk philosophy back then. So instead of having that branch less than, because you would also want a branch less than equal or a branch greater than, right? You would want all those kind of comparator operator equivalent instructions here. Instead of doing that, we put the pressure now on the assembler to say, well, we have an equivalent sequence of instructions. We covered them briefly on Friday, and this is something you have to get comfortable with eventually. Would be the equivalent would be those set less than instruction, right? set less than, that is actually storing the result of that comparison between 1 and 2. And in the interest of doing this in this, the so-called textbook way, I called it 1 and 2. Let's call it T1 and T2. We're actually doing the comparison as its own separate instruction, and we're going to restore the result of that comparison. It's a binary value. It's now saying this value, if we were to add the comment for that here, would be in AT, we are storing the result of T1 less than T2. Where if it is less than, the value of AT is 1. If it is greater than, the value of AT, or if it's greater than or equal, the value of AT is 0. We don't have to use AT for this, but MIPS does say if you, as someone working on the assembler or compiler, want to expand your pseudo instructions, one of your 32 registers can be dedicated for that purpose. And that's the assembler temporary register. That's why it's given that label of AT. But that's not really something that happens at all at the architectural level. So unlike register 0, that has explicit ISA functionality that it always holds 0, you have to implement that yourself. And register RA, which we haven't talked about a lot now, but it gets overwritten by certain instructions, even if they're not mentioning that instruction or mentioning that register. The AT register is not really something that you're architecturally implementing. It's more of, if you plan on using assembler pseudo instructions, here's a register you may want to consider using to store temporary results here. You yourself, though, as you're assembling the code, could use whatever register you want there and it would work equally well. We're not done. This is just setting that value of AT. We want to branch if AT is 1. And I mentioned on Friday that sometimes you have to deal with some double negatives as you're dealing with branch comparing to 0. We want to branch if AT is equal to 1. There is not a branch equal to 1, but there is a branch not equal for which you can just use 0. And that so-called pseudo assembly, pseudo instruction expansion, I mentioned Mars already. Mars will do that for you as well. So you can code in Mars, at least, with branch less than, even though it's not a native MIPS instruction. It'll put that in there. It'll put that in there instead. If you're working with a compiler that's starting just on high-level assembly code, depending on the level of optimization you're asking, it may be even more clever in terms of how it's going to assemble it down to native instructions. But that is, the big picture is there is that sort of a design philosophy or a design trade-off that instead of supporting n different branch instructions, the MIPS philosophy was, let's have a very small number of branch instructions. So fewer opcodes, fewer bits needed for our opcodes, easier to squeeze things into 32 bits, I would imagine. And then let's have more dynamic instructions needed at runtime to support those relatively brief conditions that we would want to compare against. Any questions about that? Because that is one of the big pictures of this course. Now, I'm never going to say that the MIPS decision was right or wrong. It's an appropriate decision for the time and place of when MIPS was designed. Makes our life easier, right? We don't have to do anything in VHDL with regards to pseudo instructions. We have to be aware they exist. We have to write assembly code that uses them effectively, and we understand the implications of them. We don't have to touch the VHDL for pseudo instructions. It puts more pressure on either the compiler, the assembler, or the assembly programmer to be able to use those pseudo instructions, makes your architecture relatively simple. But each ISA explores a different trade-off in that design space. There is no right or wrong answer with regards to that. So we talked about just simple if statements. We can also look at more complex control flow in C and what that would correspond to in our MIPS assembly. So consider the while loop on this slide here, where you're checking while a of I is equal to k, and then if it is equal to k, we just increment I as I plus j. So it's not just a single branch, it's going to be a loop, right? And the simplest kind of loop are those while loops here. This is kind of combining two concepts, right? We have to check if a of I is equal to k. So first we have to do the array index of our a of I. So that's what that beginning of the logic is doing here, right? There's that shift left logical, which I know looks like set less than, but it's totally different instruction, right? That's our shift left logical of taking the value of I and shifting it to the left by 2. That's our I times 4, right? That's multiplying by 4 because we're taking this I, we're assuming these are all integers, I guess. Problem didn't state that, but that's our assumption that because these are integers, we multiply this by 4 to get the number of bytes in our offset. The add instruction is then going to take that I times 4 value and add it to our base address to calculate now the address of A of I. We now can then do our load word instruction, right? This was our design pattern I said you were going to see just over and over again. Every time you see A of I, you're going to see those 3 instructions. And the amount you shift is a function of how many bytes each element of A is going to be. Even if it's A of something much, much more complicated, ultimately it breaks down to something called A of I, and then you'll see those 3 instructions ultimately. But now we have A of I. We now need it. We've loaded it. It's now stored in register T2. We now need to check if it's actually equal to the value in the register corresponding to K, and that's where our use of the branch either equal or in this case branch not equal instruction. Hey, I'm inside this while loop. If A of I is not equal to K, I need to get out of this while loop. So I want my next instruction to be whatever is here. We don't show any additional instructions, but assumingly there's something interesting, the code continues below. For now, we just show sort of an empty label. That's fine. But branch and get out of this loop if that equality condition is not true. If it was true, then we have our fall through. They were equal to each other. They were not equal. I mentioned double negatives being a common thing here. If they were equal to each other, then we would actually implement the inside of that loop. I equals I plus j. We're not quite done, at least in this encoding of the C sequence down to its assembly equivalent, because we've gone through one time through the loop. It's not the same as an if statement. Now we're going to continue through that loop. So we need to get back to our loop. In this case, if we've executed this instruction, meaning we're inside the body of the loop, it's not really conditional anymore, right? No matter what, if we're inside the loop, we should go back to the beginning of the loop when it's over. And that's why you have that jump, that unconditional branch. Get back to the beginning of that loop. You're good to go at that point. It's slightly inefficient. I don't want to belabor this point too much. Something we will learn certainly over time is that branches are extremely expensive. And that's an important big picture concept from this class is understanding computing performance, that arithmetic can be done blazingly fast, but branches are slow in our 1992 processor we're implementing in this class. They're equally slow and painful in our 2020 processors as well. So as a possible optimization, while it's still a little hand wavy to say, why exactly that's the case, a possible optimization is to look at this implementation of the while loop and say, well, you have 2 conditional instructions each time you go through the loop. There's a condition check, and then there's that jump back. And both of them are going to be quite expensive to implement in terms of our software performance. If it were to be possible to implement this same loop with just a single condition as we're in our steady state of iterating through the loop, it is true, although I'll keep it a little hand wavy for today, it is true that the performance of that code on the right would be decently better than that code on the left. So we can actually remove that jump from the loop body itself by directly just jumping into the condition check itself. So it's not quite the same as transforming a while loop into a dual while loop, but it's kind of the same thought process you're following. How do I restructure my loop in the C code, in that case of while to do while, and in the assembly case here, so that we're not just branching as much. So in this case, what we're doing is recognizing that while the previous example was checking a condition and then always going back to the loop itself, we can use the branch condition itself to decide whether we're staying inside the loop, and it's can serve both purposes. So in order for that to be correct, because it's a while loop and not a do while loop, we got to make sure we jump to that condition itself to begin with. That requires an additional label, but labels are free, right? Labels are just an assembly programmer's way of keeping track of which instructions you potentially want to jump to. So in this case, and again, it was visualized with the control flow graph on the previous slide, we're going to jump directly to the code to determine the condition. And then our steady state is continue in that loop body and keep checking that code. Our steady state has just a single branch versus this steady state that has two branch or a branch and a jump every time through. And that's all that's being shown here. So it's the same exact instructions as the previous example. We just jump to that condition to start with, same A of I. The difference now, because we're branching to determine whether we want to stay inside the loop, we're no longer branching to exit, we're branching back to the loop itself. So it's actually going to be a branch equal and not a branch not equal. I mentioned that a couple times now. It's very possible to get stuck with double and triple negatives as you're trying to figure out whether it's an equal and not equal and so forth. Certainly when you add those set less than operations as well. Usually it's a pretty easy thing to check. If your branch condition is exactly backwards, you test your code and you see that, well, I was supposed to go to the branch and I didn't. I just need to change my branch equal to a not branch or to a branch not equal. So let's try to understand the performance of our code and use some of the appropriate terminology to do so. So this is an example that's going to require more lines of code, but it's arguably simpler than the while loop example. So if I were to say, as a homework or an exam question, take this for loop and convert it to the equivalent assembly. Um, this is how you'd want to start, right? Assume something about the data. Either I have to tell you something about the data explicitly or implicitly through the data types as they're declared, or you have to just state your assumptions and say, yes, I'm going to assume that each data is just 1 byte each, um, as well as some assumption of where your variables are getting mapped to in terms of your registers. Again, either I tell you, assume that I is stored in S0, or you say, these are my assumptions as I'm writing this code. It really helps in terms of the readability of your answers. It's very quick to grade when we see those, excuse me, when we see those assumptions, knowing that, okay, it's following a logical flow here. But whether you're not here at that point conceptually today, very soon, by the end of homework 2 or certainly homework 3, you should be able to do that translation. We haven't done a lot of it together using our time together in class. That's what the homework is, at least in part 4. But I would expect you by the end of next week to be able to take this code and directly translate it to our MIPS equivalent. And here is an example of one way we could do it. Sometimes these can be a little tricky to grade because there is more than one way we can do it. There isn't one guaranteed, only one correct way to map that C code to assembly. This is a pretty straightforward logical way of doing it, but there's other ways that would have been valid as well. So we have our for loop, and we have to keep in mind that the for loop is doing multiple things, right? In this case, it's initializing an index array I equals 0. It is checking if I is less than 32, and then if it's not, it implements or it executes the code inside that loop, and then ultimately increments I before doing that check again. Um, Implicitly, I think we know that when we write our C code, but logically, it is correct that this initialization happens first, then we do the condition check, then we do our loop, followed by our incrementing of our loop index variables. And that's what that mapping down to our assembly code is showing here. So we start with that initialization of I. That's just one way to initialize I to 0. There's many ways we could do it. Whatever the value was in I, subtract it from itself, and that stores the result back as 0 in register S0 corresponding to I. Then we actually do need to do our condition. Even though you look at that and say, well, I is 0, I is never going to be less than 32, and maybe an optimizing compiler then gets rid of that one check or not. In terms of a literal interpretation of what's happening here, we initialize I, we then check to see if the condition is going to be true or not. If the condition is true that I is less than 32, we then go into our loop where we're executing this code, where we calculate offset into B. We do a load byte because it's just a single byte entity now. We add that result to J. We then do the same thing for our A of I, where we calculate the offset into A, and then we store the result that was the result of our addition back into A of I, increment our loop index, check the condition, and just continue. There's no shift left logical here because explicitly you're told as part of the problem setup, or you're assuming if I don't tell you that these are just single byte entities. Because they're just single byte entities, A of I, the address of A of I is equal to the address of A, the base address, plus I. It's not plus 2 times I or plus 4 times I or anything like that. It's just plus I. So in terms of our design pattern for loading stuff, it's a little simpler in this case. There's no shift left logical. Just add I to the base address to get the new address, and then do a load byte because we're just loading a single value into our register there. Same for the calculation for the A of I. It's a store byte instead of a load byte, but we're just doing an add and then the store byte operation. That is our basic for loop that we would have here. Initialize our index, our loop iterator is the right word for it. Initialize our loop iterator, check our loop condition, and then loop through this code and doing whatever within the for loop for that. And you don't need to have that perfectly understood today, but by the end of next week, that's kind of the assumed baseline MIPS assembly understanding that you will have. There's no way I can magically grant that to you other than just through practice. And through practice, as well as having the simulator open to see what those instructions correspond to see how those what is valid and invalid in terms of the structure of these. That's the only way you can really try, through doing homework questions and through just practice. So what about the performance of this code, though? And that's a secondary but important consideration here. It's been hand wavy so far in terms of the instruction count and whether those instructions are inefficient to implement or efficient to implement. And it's still going to stay hand wavy for a while here. But at the very least, we can look at the code and we can measure a couple things about it. Assuming no pseudo instructions here, and these are all native instructions, we can look at that and based on our understanding of how this code would execute, we can determine two things. One would be the static instruction count. Versus the dynamic instruction count. Both are important, but they're measuring two different things, and this is a common term of art in computer architecture, or just understanding program implications and performance. Static instruction count would be how many instructions do I need to store in my instruction memory for this? On disk, how much storage does this application require? There's implications for performance there beyond just number of bytes of storage that I need, but certainly it's a storage metric as well. So how many static instructions for MIPS then corresponding to calculating the corresponding number of bytes becomes a very straightforward thing because we know that each instruction is going to be just 4 bytes long. So in this example, how many instructions statically does it require? Your task for doing that is pretty trivial, right? You're just adding up the number of instructions that would need to be stored in our instruction memory. Watch as I add it up here. Wrong. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, I believe. 10 static instructions for this. So to store this code in memory would require 40 bytes. Take my word for it that does tell you something about performance of this code, but not that much, and certainly not that much yet. That's our static instruction count. How many bytes do I need to store this in instruction memory? It will impact performance at some point. For now, we just keep track of that and move on. Dynamic instruction count is as this code is executing, how many instructions do I need to fetch, decode, and execute to get through this? So you could also call the dynamic instruction count the runtime instruction count, or just instruction execution count. Dynamic just refers to not just what is it stored offline on disk or in memory, it's as it's executing, how many of these instructions are being fetched. And there I think you could see that would have a direct impact on performance because each instruction is going to take a certain amount of cycles. We'll get some better verbiage for this as the semester goes on, but each instruction requires a certain number of cycles. And so more instructions is potentially, worse performance, potentially at least. So in this case, though, it's kind of sort of similar to as you start to take algorithms classes. And many of you I know would be in 310, CPRE 310 right now. You do that big O analysis of your code. And there's a corollary there. But here, typically, as we look at both our C code and certainly as we look at our underlying assembly code for it, we tend to be able to measure it precisely. assuming some relatively straightforward assembly code examples, we don't have to say, well, this is a single for loop, so this is, and assuming, let's assume this is n and not 32. That makes it a little bit more interesting. This is big O of n because it's kind of a single for loop. That's correct, and that's useful for algorithmic analysis. But even if we just have n as an input variable here, we can look at this code and directly measure how many instructions it's going to take to execute. We just have a couple minutes, so I'd like you to take a minute and think about it for this particular problem. So static, I told you it was 10 instructions. I need to store 40 bytes in memory to store this code. Dynamically, at runtime, and just think about it for a minute, how many instructions is that going to require to fetch, decode, and execute? It's more than 10, right? Because it's a loop. But how many would it be? How would we calculate that? How would we go about doing that? Don't all shout out at once. I'm sure internally in your mind space you have it all completely figured out. That sounds promising. Some of the things that I'm reading there. Yes, actually, that's both of you are correct. Okay, you got it. Great. Um, that's 2 out of 154. So my job here is done, and we all successfully understand this concept. The two is the first part of that answer. We have these two instructions that are definitely kind of um, stub instructions here, and so your answer is close enough. That no matter what, we're executing those two. And then, as we go through the loop, what's going to happen? That first time through the loop, we're going to execute these two instructions. So we're actually not just guaranteed 2 plus something. It's actually going to be, let's see if I can get back to my window here. It's actually going to be 4 plus something, right? Because no matter what, that first time through the loop, we're going to be calculating or executing, fetching and executing this instruction and this instruction, as well as this instruction and this instruction. That's our initial condition, no matter what, that's the case. But then we have our steady state of, okay, the branch was taken, we go back into this loop, and then inside that loop, we're executing 1, 2, 3, 4, 5, 6, 7, 8 instructions. So 4 plus 8 times n is a good answer to that question if it was iterating n times, where n, if it's 32, would lead to a result of 260, right? So 8 times 32 plus 4. 260 instructions is the dynamic instruction count. We unfortunately have to leave things here for today, but when we pick things back up on Wednesday, I want to explore briefly, we have whole separate classes that cover this, what the compiler or you as the compiler could do to improve upon that number, to look at that 260 number, and whether or not the total number changes, we can potentially change the instruction mix that is within that 260 instructions. As I mentioned, that branch instruction is potentially problematic from a performance perspective. Can we rewrite this code that it doesn't require 33 branches? Can we do so with significantly fewer? And we can briefly at least talk about what the implications are of doing that. So let's leave things for here for today. The only final thing I want you to remember is you have that Lab 3 pre-lab, and finding your team could be a little stressful for you, but I'd like you to try. And if you don't get it done before the beginning of your lab this week, we'll just use the first few minutes in your lab to assemble teams. I think you're better off if you're picking your team versus we just put you in a team. But if you can't find one, I'm happy to do that as well. And taking a look at that team contract will help as you assemble your team. That's not due by the start of the week 3 pre-lab, but I'd like you to be thinking about it because you're really determining, is this going to be a successful team or not? What does it mean to be a successful team? You've seen that there's some difficulty level of these labs. Yes, I'm giving you teams now, but the difficulty is also potentially, or the amount of work is potentially increasing as well. So take that task seriously, and I think you'll have a better overall experience in this class this semester. Otherwise, I'll stick around for a little while, but it's good to see everyone again, and I'll talk to you all on Wednesday. Thanks.